Hello, today we're going to be looking at sketching a specific type of graph today. This type of graph is called a rectangular hyperbola. Right now you may not know what they look like, but we're going to talk about them and see what they look like when we start plotting them on the Cartesian plane. Now, one of the ways to investigate how a graph could look is simply just to come up with a table of values. For this specific case, before we actually come up with the table of values, which if you don't know what they look like, this is what it can look like. Here's your x values, here's your y values, and you just set a group of x values and a group of y values, or a group of x values, and then determine the y values and get your coordinates. But before we get here, we need to consider a very special case for this specific equation. Here we have y is equal to 1 over x. Now, this brings up a very special case because we get to a point where we look at what happens when x becomes 0. If we divide by 0, we actually end up in a special case where we have a undefined value. We can't actually define it. If you can put it into your calculator, it'll come up with syntax error, and it's not something that we can actually plot. Now, we will keep that in mind as we come up with a table of values, because we're going to cross from the negative end of the spectrum to the positive end on the x-axis. So we'll come up with a series of values, so we'll try and see what happens when we do so. So we have, let's come up with -2, -1. We'll do -½ as well, just to sort of see what happens when we get in between 1 and 0, -1 and 0. So we'll have 0 as well, and we have half, we'll have 1, and we'll have 2. You can see it's symmetrical in this case, all right? And we'll figure out what the y values are when we put the x values in. Okay, so let's try that. So I'll just do a sample calculation so you know what I'm actually doing on the side. So I'm asking the question, what does y equal when I substitute x in? So for example, I'm substituting now -2 in just to see what happens, and that just becomes y is equal to -1/2. So I can write that down in the table of values as -½ Okay, same thing, plug in -1, x equals -1 into the value, I get -1. Plug in -½ okay, so if you haven't seen this before, this is y is equal to 1 over -1/2 or 1/2, and we know, well, if you do your fraction operations properly, this is -2, so we put -2. Okay, this is undefined, so we can't actually have anything in here. This is half, so we put the half in. This would be +2, this would be +1, and this would be +½ And then we can actually plot these points onto the graph and see what the features of the graph actually look like. So here my table of values will plot the graph now. Okay, so we'll just make this one, we'll make this 2. I'll make this, so put 2 a little bit further. Here's 2. Okay, we'll have this as 1, -1. We'll have this as -2. Okay, and of course we'll have -½ here, -½ So this is just a half, -½ and we can start plotting some values. Okay, at half, when it is equal to half, this is equal to 2, so we can go to here. The 1, so this is about 1 here, and at 2 we have half, so that'd be around here. Okay, that's what it looks like on this end, on the positive end of the x. Let's try see what happens on the negative end of the x. When x is equal to -½ here we have 2, so this would be down here. -1, 1 is about here. Okay, and then we have around here. And we can see that this constructs a really strange shape. Like usually when we're doing a quadratic, these things connected, but this doesn't work like that. Okay, these things actually doesn't connect. In fact, if you investigated the values in between -½ and ½ and 0, you'll find that these values keep going upwards or downwards towards infinity when that happens. So what you end up with actually looks something like this. So here's your graph. We'll go here. Here's your graph, and here's your graph down here. Okay. What's happening here is, as we get closer and as x gets closer and closer to 0, the graph shoots towards either infinity if we're on the positive end, or negative infinity if we're on the negative end. And in the same case, interestingly enough, as x approaches infinity, this thing approaches 0 but never gets there, and this thing also approaches 0 but never gets there. I guess I'll try and show that. So he'll keep going until it flattens out and never gets to 0. Now this constructs what we call what we have are some new features of what we call here. These things are called hyperbolas. Okay, they're different from parabolas that we worked with before. Hyperbolas look like this. We have 2 ends. Sometimes people call these bows, okay? And they're called rectangular hyperbolas because of a specific feature that they have. I'll do it in a different color so that you can see them, okay? I'm going to show you these 2 lines, and I'm going to draw them in a different color so that you can see them. Here's one of the lines in dotted, and here's the other dotted line. Now, what these lines represent, I'll show you. This is y is equal to 0, and this is x is equal to 0 here. What these lines mean, they're called asymptotes. I think I can spell these. Asymptotes. These, let's see if I spelled that correctly. Asymptotes. Yeah, I got it. Great. These things, these lines, represent a certain line that shows us how this hyperbola gets closer and closer to those values as x goes up or as y goes up as well, but never reaches and never touches. This graph never touches the asymptotes, it simply approaches them. And so we have 2 types of asymptotes. We have a horizontal asymptote, okay, because you can see that that creates a horizontal line, y equals 0, and we have what you will guess, vertical asymptotes, okay. These are a key feature of a hyperbola, because when you start drawing different hyperbolas, you need to know where the asymptotes are, and once you know where the asymptotes are, you figure out the intercepts and you can come up with a graph. So here is an example of what these can look like. We have down here an explanation of how we find the asymptotes using a specific set of form, okay, a set of specific form. Here's the form you need to pay attention to and be aware of, okay? You need to be constantly aware when we're working with these hyperbolas of this specific form, okay? This is the form you need to understand. These values, h and k, tell you what the asymptotes are. So in this case here, we have when the h value is the h value tells you where the vertical asymptote is, and the k value tells you where the horizontal asymptotes are. Okay, now I can illustrate this for you through the use of Desmos. So here we have Desmos, and here we have a hyperbola. We can see here y is equal to a over x minus h plus k. In this case, I got h is 0, k is 0, and a is 1. So this graph is actually exactly the same as if we did y is equal to 1 over x, because a is 1, x is x, and h is 0, so it's x minus 0, which is x, so it's just 1 over x. This is what it looks like. This is the same graph. If we go back to here, this is the same graph we sketched over here. Now, what we can do with this graph is we can see what happens when the h value and the k value changes. You can see here that the asymptote, the vertical asymptote, is at x is equal to 0. You can see here the lines approaches that line but never gets there, and also y is equal to 0, which is horizontal asymptote, because it never reaches. You can see if we can go up and up and up, but it never actually touches there. If I can zoom in, it never actually touches, okay? Now, cool thing about this is, as h goes up, the asymptote also goes up. So you can see here as h is equal to 4, the asymptote turns into x is equal to 4, which is the vertical asymptote. Okay, you can see here the line adjusts itself based on what the h value is. So the h value tells you where you should start horizontally to get you the vertical asymptote. Okay, that's what the h value does. And of course, the k value tells you vertically where the horizontal asymptote is. So if I have it at k is equal to 2, then the actual asymptote is the horizontal asymptote is y is equal to 2. And so by knowing these 2 values, you know where to start with your sketch, and this a value gets us a lot of information as well. The a value actually, we call it dilation. As the a value goes up, the 2 bows here go further apart, and funnily enough, if this a value becomes a negative number, it actually reflects the opposite way. So it looks like this. Okay, it goes this way. Okay, you can see the top reflects on the vertical axis and the bottom reflects on the vertical axis. Okay, And this is some key features we need to know. We need to know the dilation with the A value, the H and the K value, which tells us where the asymptotes are to know where we should start drawing these. And we can use these to start drawing specific hyperbolas. So we can try this one first and go from there. Sketch the graph of y is equal to 2 plus 1 minus 3. Now remember, we have this rule, and this rule tells us a lot of information right now. It tells us, as soon as we look here, what the vertical and the horizontal asymptotes are. So I'm going to draw the graph straight away. Okay, I will just draw a Cartesian plane. This, okay. Here's our y value, here's our x value, and we can just start. Okay, we can know that here x minus 1, sorry, x plus 1, which means that here the h value is equal to negative 1. Okay, I'll just even write it here so you can see. The h value is equal to negative 1. Okay, which means that we have our vertical, we have our vertical asymptote. Our vertical asymptote is here at x is equal to negative 1. Okay, so we can go, well, x is equal to negative 1, we can just define where that is. Let's say it's here. We'll just do this. So there's our vertical asymptote. We can just write this as x is equal to, oh, actually it's negative 1, so I should be going the other way. My apologies. Negative 1. So we're going to go here. Okay, x is equal to negative 1. That's your vertical asymptote, and then we can have horizontal asymptote, which is also negative 3 here. So here we can go down here and say, well, this is about here. Okay, and we'll just do this. And we have our y is equal to negative 3, which is our horizontal asymptote. Okay, here we have our graph ready to draw. I know it doesn't look to scale, but we'll work with that a little bit later. Now, what we can do here is find some specific features. Because they both have because this thing has a horizontal asymptote and a vertical asymptote, we can actually look for key features that we've looked for before, like the x-intercept and the y-intercept. So we'll do y-intercept first. Okay, y-intercept is when x is equal to 0. So we just have to find what the y value is when x equals 0. Y is equal to 2 over, well, substituting 0 in, plus 1 minus 3. Okay, so this becomes negative 1. So when x is equal to 0, y is equal to negative 1. So in this case, we can actually write that down when x is equal to y is negative 1. So this is 3, so we can just sort of try and put it there. That's where one of the lines will be. The other line will be when we can find is the other point is called the x-intercept that we can find. So that's when y is equal to 0, and we can find this value because they have the asymptotes. So we can go y is equal to, oh, actually y is 0. So in this case it will be 0, and then we can go 2 x plus 1 minus 3, and then we can solve this algebraically. Put the 3 on the other side is equal to 2 over x plus 1. Okay, I might just flip this. I think that may work. So I'm going to flip. So this is 1 over 3 is equal to x plus 1 over 2. Okay, so I'm going to times 2 over on the other side. So this becomes x plus 1 is equal to 2 over 3. And of course, I'm going to subtract 1 here to get x is equal to negative 1 over 3. And you can, there's a different way to approach algebraically, but you will get the same answer. So when y is equal to 0, the y-intercept, oh sorry, the x-intercept is negative 1 over 3. So here we have, well, this is, when do we put 1? Negative 1 over 3, so it'd be probably about here. Okay, and here we have the beginning of our hyperbola. We have 2 points here, and we know it's going to approach this line but never get there, and we're going to go down this way, and then we know it's going to approach this line and never get there. Good thing about hyperbolas are that they're symmetrical in the sense over here. You can see that they're symmetrical, so if you can draw one, you can draw the other straight away, and so we can do that by simply going, well, if we extend the asymptotes, we can see what that would look like. Here is what it would look like this. And there you go, we have our graph. We identified first what our asymptotes are, okay, our horizontal and our vertical asymptotes, by using the values over here. So let's just get those values correct. This is one here, this is one here. I looked at this value to determine that first value. I looked at this value to determine the second value, and then that gets my asymptotes. I then determined my y-intercept, x-intercepts, and I was able to gain an understanding of how to sketch the graph. So hopefully that gets you started in drawing some more, and I might do a few examples a little bit later for you for your viewing. So hopefully that helps. Have a great day. See you later.